In today's lecture, we will learn about counting the spanning trees of the complete graph. So, let us understand what this means. So, we have talked about spanning trees before. So, suppose G is a graph, a spanning tree T should satisfy two conditions. The first condition being T should be connected and the second condition is T should be cycle free. Okay. So, it is basically a tree such that every vertex, there is a path from every vertex to every other vertex. So, you can say that it is the minimal such graph, minimal in the sense of number of edges required. Okay. So, this is the definition of a spanning tree, and we are looking at the complete graph on n vertices. So, let us say if we had taken 3 vertices, this would be the complete graph on 3 vertices, which we represent by k3, and if we number the vertices as 1, 2, 3, this graph has many spanning trees. In particular, if we just try to draw, every spanning tree of this graph will have exactly 2 edges. So, 1, 2, 2, 3 is one possibility. So, this is T1, one 3, 2, 3 will be the second spanning tree, and there is yet another spanning tree which is 1, 2, which consists of the edges 1, 2 and 1, 3. Okay. So, we can verify that these are the only spanning trees for K3. So, when k equals 3, the number will be 3. If we had looked at the simpler example of K2, it is precisely one spanning tree. So, you can say for n equals 2 the value is 1, for n equals 3, let us see what is the case when n is equal to 4. So, we are looking at this particular graph, the complete graph on 4 vertices. How many spanning trees does this particular graph have? So, we can enumerate them. So, one would be of this kind where, so all the spanning trees of K4 will have precisely 3 edges. So, the ones which consist of the boundaries of the square, there will be 3 of them. So, there is a missing edge here, and there are 4 ways you could choose them. So, there are 4 trees of this kind, and if you include the diagonal, okay, so you can include both diagonal. Okay, so, these 4 are without including diagonal. Now, the choice becomes, do you include 2 diagonals or do you include only 1 diagonal? Okay, so, let us just look at including 2 diagonals. So, these are the 2 edges, and the third edge that you want to add could be any of the other 4, okay, because each of them. So, if you had taken this, that will give you a spanning tree, and so all those 4 choices would give you valid spanning trees. So, there are 4 trees of that kind, and if you choose to include just one diagonal, okay, so let us say if we are using the 1, 4 diagonal, the other case would be symmetric. Okay. Now, we can choose either these 2, this is yet another case, so these are the 4 spanning trees that we will get if we choose to add the 1, 4 edge. If we insist on having the 1, 4 edge, you could add 2 the degree of this particular vertex 1 could be 2, in which case the only possibility is this, the degree could be 0, in which case this is the only possibility. The degree is 1, there are 2 possibilities, namely these 2. So, there are 4 trees when you choose to include 1 for diagonal, and the symmetric case would be when you include the 2, 3 diagonals, there are again 4 more. So, the case where n is equal to 4, the number of spanning trees is going to be 16. You can imagine that it is going to be extremely time consuming if we were trying to do this same thing for n is equal to 5. So, what will be the number when n is equal to 5 and so on. So, this is what we need to understand. Okay. We need to count the number of spanning trees of the complete graph on n vertices. Okay. And we will do it via a method known as proof or coding. Okay. So, you can look at these numbers and see if you can detect a pattern there. In any case, from proof or coding, what we know is the number of spanning trees of kn. So, we are looking at labeling kn. Okay. So, these are, and after we have obtained the labeling, how many distinct spanning trees are there, that is what we want to count. The number of spanning trees of kn is equal to n raised to n minus 2. This is the theorem that we would prove. So, our count is n raised to n minus 2. We can verify that when n is 2, 3 and 4. So, 2 raised to 2 minus 2, that is going to be 1, 3 raised to 3 minus 2 is going to be 3, 4 raised to 4 minus 2 is going to be 16. Okay. So, all those cases we have verified, and we need to prove this in the general case. And while proving this, we will use an interesting technique. We will basically set up an isomorphism between 2 sets. Okay. So, let us look at this problem. You are given a particular set S and you want to count the number of elements in it. One way to count is to explicitly count the number of, enumerate the elements in S and then see what is its count. Another way could be to set up a correspondence. Okay. So, you can set up a correspondence with another set which is easier to count. Okay. So, this we can think of as an easier to count set. If we can find an isomorphism which maps every element to a unique element in the other collection, okay, in such a way that every element of the other set is occurring as the image of at least one of the elements. If we can set up a bijection between these 2 sets, then we know that the counts are going to agree. So, there are many natural objects whose count is n raised to n minus 2. We will show that the spanning trees can be put in bijection to one of those sets. So, one natural candidate for a set having n raised to n minus 2 elements would be, if you consider lists, okay, we will think of this as an ordered lists of size n minus 2 from a set S consisting of n objects. Okay. So, we have a set, let us call this set as S. Now, this set has n objects and we are allowed to form list of these, and the length of these list is n minus 2. The first element of course can be chosen in n ways, and we are allowing repetitions. The second element also has n possibilities. The n minus 2 element can also have n possibilities. So, they multiply, and therefore, the total number of ways of having these lists clearly is n raised to n minus 2. Okay. So, this is one of the quantities that we have. Now, we have this collection of the set, our main set that we are interested in, let us call it as T. T consists of all the spanning trees of Kn. Okay. So, if we are able to find a bijection such that each such list corresponds to one unique element of the set of spanning trees, then what we know is that the counts match. Okay. And this bijection is basically known as the proof for coding. Okay. So, let us see what is this bijection. The bijection will be given via means of an algorithm. Okay. So, we will assume that we are given a tree. So, input is a tree whose vertices are from the set S. Okay. And we are going to assume that the set S is an ordered set in the sense, given two elements of the set, we can say which is the larger element, which is the smaller elements, and so on. Okay. So, we will assume that there is a total order on the set S, and the output will be a sequence of length n minus 2, or a list of n minus 2 elements So, proof for coding basically, when given an input tree, it will produce an output sequence. What we will need to show is that every sequence will be generated by precisely one tree. When we look at this encoding, when we look at the algorithm for encoding, we can see that if you are given a tree, there is only a unique sequence that can be produced. The sequence produced will be unique, but what we will argue is that for every sequence there is a tree which generates that as well, and there is precisely one tree which will generate that. So, let us see what encoding is. So, the proof for code is generated in an algorithmic fashion. So, this is the iterative step. Okay. So, we will repeatedly do this iterative step for n minus 2 steps. What we do is pick the least valued leaf node. Okay. So, you are given a tree, so the tree must surely have some leaf nodes. Amongst the leaf node, find the smallest valued leaf node, delete that node along with the edge that it is along with the, so since it is a leaf node, it is connected to one node, delete that particular edge. Okay. And output the neighbor of the deleted node. Okay. Since it is a leaf node, its neighbor is unique, it is precisely one neighbor, so that neighbor we will output, and we repeatedly do this for n minus 2 steps, we get a sequence of n minus 2 elements. So, the easy fact is every tree produces a unique list of n minus 2 elements. Okay. So, if you give a tree, the answer is unique, but it could happen that two trees could give rise to the same list. It could also happen that certain list cannot be produced by any tree. We will rule out both these cases. This fact is obvious, the fact that every tree produces a unique list is obvious, because the algorithm has no randomness, and at each step, since the least valued leaf node is picked, that is unique and its neighbor is also unique, and therefore, if you give a particular tree, the output list is automatically fixed. Let us work this out for an example. Okay. So, suppose we look at this particular tree, the leaf nodes are nodes 1, 7, 5 and 6, and the least valued leaf node is 1. So, we will delete that, and its neighbor is 2. So, that is what we will first note. Okay. And now, if you look at the remaining tree, the least valued leaf node is the node number 2 or the vertex number 2, and its neighbor is 4. So, we will remove this and we will write out the number 4. Now, amongst the remaining nodes, the leaf are 5, 6, 7 and 8, the least being 5 and its neighbor is 3. So, we will basically remove 5, and after that we will remove 6, 7. After we remove 6 and 7, when both their neighbors with 3, so when 6 is removed we get a 3, when 7 is removed we again get a 3, and at this point the tree consists of 3, 4 and 8. And if we look at the leaves, there are precisely 2 leaves, 3 and 8, the least valued one is 3 and its neighbor is 4. Okay. So, this is the sequence that we get. Okay. Now, what we will claim is, if we know the underlying vertex set, from that information and from this numbers 2, 3, 4, 3, 3, 4, we can recover back the tree. So, I hope this process is clear. We can just, the iterative step is, at each stage pick the least valued leaf node, delete the edge corresponding to it and note the neighbor of the deleted node. Okay. So, let us just look at the sequence 2, 3, 4, 3, 3, 4 and try and generate the tree back. Okay. So, suppose we know just this information and we do not have access to what was the original tree. From this, can we recover back the tree? If we look at the sequence, one thing that we know is, there are 2 facts that we can note. Every leaf node will be absent from the proof or code. And the second aspect is, every internal node will be present in the proof or code. Okay. Why is this so? The leaf node, the only numbers which appear in this are internal nodes. That is because the leaf node is a node that you are going to remove, and when it is removed, the node itself is never written, but its neighbor is written. So, anything which appear in the proof or code, at some time it will have to be an internal node. So, we can clearly see that the leaf nodes will be surely absent from the proof or code. If you look at the process of generating the proof or code, we are starting at a tree and we are systematically removing the edges. So, there will be a point at which any node, its degree will keep on decreasing, and there will be a point when it becomes either 0 or 1. In the process of generating the proof or code, we took a tree and we were removing the edges one after other. If you look at the initial tree, the process of generating the proof or code basically removes an edge from the tree, one edge at a time. So, every internal node is going to lose some of the edges corresponding to it, and when this happens, that node is going to appear in the proof or code, and therefore, we can argue that every internal node will be present in the proof or code. Okay. If we note these things, we know by looking at the proof or code 2, 4, 3, 3, 3, 4 that the leaf nodes essentially had to be the missing numbers. So, this is a sequence of length, the length is 6, and if the vertices were numbered 1 to 8, the leaf nodes would have been 1, 5, 6, 7, 8. Okay. We can look at the diagram and see that this is indeed the case, 1, 5, 6, 7 and 8. And amongst these, the first one to be removed would have been 1, and that should have been connected to 2. So, 1 2 would have been an edge, and if you look at the remaining sequence now 4 3 3 3 4, 2 is missing, and therefore 2 must have been a leaf node for that particular tree. So, we can say that 2 must have been connected to 4. Okay, 4 is still present, and amongst the numbers that are not present, the least one is 5, and 5 is to be connected to 3. The next missing number is 6. So, 6 is also connected to 3, and then you have 7, 7 is also connected to 3. And after this point 3 is no longer going to be present, and therefore 3 must have been connected to 4. And then at this point there is only one node that is remaining, that is 8, and that must have been connected to 4. Okay. So, from this number we could in some sense generate the tree. We have not given a formal proof, we will do that shortly. Vertex 3 is connected to 5 6 7, and vertex 4 is connected to 8 and 2, and vertex 1 is connected to 2. That was all the. So, at least in this case we have verified that things work nicely. So, let us formally prove the theorem. The number of spanning trees for Kn is equal to n raised to n minus 2. So, let us assume that the vertices are from a set S, which we will assume to be an ordered set. And let T denote the set of spanning trees, and L denote the set of lists of size n minus 2, where we will assume that size of S is equal to n. So, lists of size n minus 2 over S. Okay. What we will prove is there exists a bijection between T and L. So, we will prove this by induction. Base cases we had already checked. When n is equal to, let us say 3, we had verified that T contains, if we call this as Tn, Tn contains 3 elements, and the list also contains 3 elements. So, because what you are looking at is lists of size 3 minus 2. So, that is list of size 1 over S, and there are precisely 3 elements in S. So, the lists of size 1 are precisely 3. So, the base case can be easily checked. Now, let us assume that the induction hypothesis holds for all values up to m minus 1. Okay. Now, we want to show that for m also the statement is true. Okay. So, let us look at a particular sequence. So, every sequence on S of size n minus 2 corresponds to a unique spanning tree. Okay. So, let us look at a particular sequence. So, if we call the sequence by A, and that is equal to A1, A2, An minus 2, we will exhibit a tree corresponding to this, and we will argue that that tree is a unique tree. Now, if you look at, let us say A2 to An minus 2, that again is a sequence of length n minus 3, it is a subsequence. And if we knew which are the vertices that are under consideration here, we will inductively argue that a unique spanning tree can be constructed corresponding to that. To that spanning tree we add a particular edge and we will get the tree that we are interested in. So, that is our line of attack. So, let us look at it more carefully. So, look at the smallest number that is not present in A, okay, let us call it as x. We had argued earlier that the numbers that are missing in A1, A2 up to An minus 2 has to be clearly leaves, and the smallest of them would have been the first node that would have been removed when we were constructing the spanning tree. So, if we look at that node and call it as x, clearly x is the node, is the leaf node that was removed initially, and x would have been connected to A1. Now, if we look at this set S minus x, this is a set of size n minus 1, and if you look at the subsequence A2 to An minus 2, this sequence cannot contain x in it. This does not contain x in it because the original sequence itself did not contain x. So, a subsequence surely cannot contain x, and by our induction hypothesis this part A2 to An minus 2 is going to correspond to a unique tree T prime. Okay. Now, that tree with the edge x A1 will correspond to this particular sequence. So, T union the edge x A1, T prime union x A1, if we call this as T, T is a spanning tree whose proof or code is A. Okay, why is this so? Well, clearly if you add x A1 to T prime, it does not create any cycle because we assumed that x is not present here. So, that would make x a leaf, and if you attach a leaf to some other node, that is not going to create a cycle. So, the graph that you get is indeed going to be a tree, and if you look at the proof or code of that, that is precisely going to be A1, A2, An minus 2. Okay. So, this is basically the proof. This says that corresponding to every sequence you can get a unique spanning tree. The uniqueness comes out because A2 to An minus 2 by induction hypothesis has a unique T prime, and the only tree that is going to be obtained is by adding x A1 to T. So, the only tree that could possibly correspond to this sequence, the only graph that could possibly correspond to this particular proof or sequence or this particular code is going to be T, that is obtained by adding the x A1 edge to A2 An minus 2. Okay. So, that concludes the proof and the lecture.